to answer your question, Alex, I guess you kind of do, because we've learned that this year. Am I going to ask you? Maybe, maybe not. But you should be able to do it. You should be able to get the frequency, and once you get frequency, you should be able to get wavelength from that.
Because on the whole one, it was over one, 5, 1 and 2, number 19, you have to solve the wavelengths, and then there was an equation there.
Yeah, what they did is they replaced F with wavelength equation, that's all. So imagine this equation here, written like this. Right? Replace this F right here with 1 over lambda, because if I solve this for F, I switch these two spots, it becomes F equals 1 over lambda, and then I can take that value, plug it in there for F, and as a result it becomes this. And that's probably the equation you're referring to there. Okay, but you don't have to memorize this equation, Alex. This is going to be given to you right here. And this is on your formula sheet. So as a result, you can kind of put the 2 and 2 together. And at this point in the year, you should kind of know that frequency and wavelength are inverses of each other. They're inverses of each other. Yes?
In 25.1, 25.2, do we need to know the difference of all the models, like the Thompson model and the Bohr model?
I mean, you should have an idea, not necessarily naming them. If I say, what's the Thompson model? But if I discuss what's happening in the model, being able to draw a conclusion from that. From the gold foil experiment, we were able to conclude what and why. So that happens to be you. Everybody remember who did the gold foil? Is it Rutherford? Is that right? Is it Rutherford or Thompson? Rutherford? I think he's right. Thompson was the plum pudding model, right? I don't even memorize the names. I'm not memorized the first thing. But you should know how to draw conclusions, the physical nature behind it. So the gold foil experiment, we noticed that some of those particles bounced off the gold foil, but most got transmitted right to the foil, which told us that there was a lot of empty space in atoms. That only the nucleus was a highly concentrated density was causing those radiation waves to get bounced off or bounced back. So the conclusion from it should be important. Or if I discuss and draw a diagram of something that looks like the watermelon model or the plum pudding model, where you have a big mass of positive and the negative charges throughout, I could say, what proved that not to be true? And that would be the gold foil experiment. The gold foil experiment showed us that we did not have negative charges all embedded in the nucleus. Okay, they were somewhere else, and they have empty space as a result. So the ideas behind them, yes. Necessarily memorizing the names, no. I'm not going to be like, tell me the Bohr model or something. Okay, but knowing why they're useful.
For one of the homeworks in 25-1, you asked us to find which wavelength would be, so ultraviolet, is part of the thing.
You would have to be given a table to match it up with. So if you could find the frequency and then I give you a table, remember you had the table earlier in the year of all the wavelengths and frequencies, then you should be able to match it up. So if I decide to on the test, I would have to provide that table. But you don't have to memorize infrared is this way, or visible light is this way. What else do you want to go over? What are the 3 modes of heat transfer from chapter 10? 3 modes of heat transfer. Katie, give me one. Conduction is definitely one. That's the first one. Katie, do you remember what conduction is? Or what it involves? It involves? Yeah, contact, physical contact. Now, the 2 materials have to be different temperatures for this to occur. So when I touch the desk, we talked about this with that infrared gun, the desk temperature is like 75 degrees. Skin temperature is like 85 degrees. Skin is 85, desk is 75. Skin is 85, desk is 75, so which way is heat going? Which way is it physically flowing? Yeah, from your hand to the desk, down, to the desk. From your hand to the desk. Again, heat moves from hot to cold. Heat moves from hot to cold. Okay, this is very, very widely used physical conduction or thermal conduction when you look at any sort of cooling system. So your computer has a processor in it that generates a ton of heat. On top of the processor is what's called a heat sink. That heat sink again transfers the heat to what's called a heat pipe. The heat pipe then transfers its heat to what's called fins. These are fins. The radiator, see all these pieces of the radiator, or back here you can see the radiator better? Each of those is called a fin, F-I-N, fin. And the actual heat is being emanated by those fins. So if you take your computer apart, you'll see the heat come from the processor through what's called a heat pipe into the fins, and that's all conduction, it's all touching, and then the fan blows air over that. What mode of heat transfer is that? When the fan blows air over a surface to cool it off. That's convection. Let's talk about that next. Convection. So convection involves fluid flow over a surface. Fluid flow over a surface. So when you burn your finger and you go convection. When you burn your finger and then say you literally touch it to an ice cube, that's conduction. Now if you touch it to water, it's convection. Water is a fluid, an ice cube is a solid, right? So if you cool something down with either a gas or liquid, it's got to be convection. Now within convection, there is some conduction, by the way. But the primary mode, it's important to understand that word, primary mode. The primary mode of heat transfer for a fluid is convection. But the fluid technically is also touching it, so you do gain some heat change or lose some heat or whatever it is via conduction as well. Okay, Alex?
Can you repeat that?
When there's a fluid involved, whether it's a liquid or a gas, the primary mode of heat transfer is convection. So if you take your finger and submerge it in ice water, or let's just say water, submerge it in water after you burnt it, it's convection that's cooling it down, especially because you probably swirl your finger a little bit or blow on your finger a little bit. But when you're touching the water, technically, there's a little bit of conduction going on as well. But not compared to like you take a heat clamp it onto the desk and walk away. That's all conduction. It's touching and it's going through the desk as a result. There's no fluid flow occurring. Okay?
Would we need to explain like the conduction and convection?
No, but you should understand that I don't want you to recognize. If I ask you what is the primary mode of heat transfer and it's a fluid flow, that's definitely convection. I don't want you to confuse it as conduction because I think I talked about it, part of it is conduction, and your text refers to that as well. Okay? Convection, another example, air conditioners, right? Air conditioners work the exact same way. The air that's coming in is physically either from the cooler than the air in the room. The air in the room gets sucked into the air conditioner. The air conditioner takes the heat out of that. It literally recirculates the air as cool air, puts it back in. There's a fluid inside of the air conditioner called a refrigerant. It's pretty much Freon. Freon is the slang term for it. It's coded R134A. It's this physical substance that is easily absorbed. It easily absorbs energy. And as it absorbs energy, it starts to boil off into a gas. And then it goes through a cycle in the air conditioner with a compressor, and the compressor condenses that gas back to a liquid. But what it's physically doing is it's generating enough, or it's absorbing enough of the energy from the air to cool it down, and to circulate cool air into the room. Third mode. Oh, your question first? Go ahead. Yeah. Radiation, very good. Third mode, you got it already. Radiation, very good. Can somebody describe radiation? What's going on here with radiation? What's happening physically with radiation? This is the one that's a little bit different, right, than the other two? The other two are things that you recognize mostly on a day-to-day basis. Radiation is a little different. Maria, give me something.
The sun's rays, and they hit us, and they enter, I guess, through the
Atmosphere? Okay, so an example of radiation, sun's rays. That sounds good. I agree. Absolutely. Tell me more. They travel in waves. This is energy or heat traveling in waves. So this one is a little bit different because of the fact that it travels as waves. So photons, I gave a really corny joke yesterday, photons being traveling in light, are physically that. They're traveling as waves, right? They're physically traveling as waves. So we talked about how your body gives off heat in form of radiation. Infrared radiation. The heat signature that your body gives off is on the infrared spectrum. Its frequency falls into the infrared wavelength, so you don't have to memorize it, which is an example. And as a result, you feel body heat coming off the person. Okay, if you touch like that, that is conduction, because our hands are in contact. But if you're literally a couple feet apart, you actually feel radiation from the other person in the room. Rooms heat up. Trains warm up when you're on the train for a while, right? When you're physically on there because there are a lot of bodies on the train. And your body is taking the food you ate, saying, you know what, give me the energy from that food, and I'm going to take that energy and I'm going to radiate it outward. And it's literally doing exactly that. A fire, a bonfire, a good example of heat transfer. The coals themselves that are like glowing red hot radiate heat outward. Now, as you stand next to the fire, though, you feel like fluid or like hot air on you. That's convection. So a fire pit is radiation with the coals, convection that you feel from the air around it warming up. And if you physically were to touch the coals, conduction, right? That would be conduction, or touching. When you throw a log onto the fire, that transfers its energy into the other log, causing combustion, but via conduction, the increase in heat via contact. All of these things are specific to materials. So there are certain materials, and I kind of alluded to this and talked about it a little bit, but there are certain materials that are better thermal conductors than others. And we referenced in class metal as one of them, and I talked about how if I touch this metal chalkboard ledge, it feels colder than the desk does. It really does, it physically does. That's metal. This is some sort of a polymer or some sort of resin, I think that's poured. So this material is very different here than thermal conductivity. This has the thermal conductivity is much easier to transfer heat in metal than it is in other materials. So as a result, you lose a lot of the heat in your body here. It has a high thermal conductivity. I didn't get into the math of this, that's why I don't want to talk about higher or lower. But higher thermal conductivity means you lose heat quicker. You lose heat easier. It's a higher, what's called K value. You don't have to know that, I'm not going to test on that. Same thing with convection. Fluids and surfaces have what are called convective coefficients. So for example, air flowing over a surface versus water versus liquid nitrogen versus a refrigerant, they all have different values for convection. It's an inherent property. So it's a material property like density, viscosity, friction. Those are all material properties. Same thing with conduction and convection. We have what are called conductive coefficients, convective coefficients. And then radiation is a little bit different. And radiation does not involve a specific coefficient. We're not going to get... The math for radiation is not hard, but it's something we have not studied at all. Talking about what's called black box radiation. And it's a comparison, really. It's more of a ratio, actually. That was chapter 10 for modes. Chapter 10 for modes. We have chapter 25 we haven't really gotten into too much of. There's a little bit of math. There's the models of the atom. There's the theory behind the math. And then the rest of chapter 10 is mainly math, right? It's mainly math. Some more theoretical stuff, like what is thermal equilibrium? Physically, what is it? You know, heat always goes from hot to cold. We call that a temperature gradient. Knowing the word gradients, I've used that many times now in this class. A gradient is like, hey, this is really hot because I apply heat source. Cooler, 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 cooler. And we talked about heat signatures. And I showed a diagram of that where this was red, then it was like orange, yellow, green, light blue, dark purple. And those show different levels of temperature on the surface of that object. So I use the phrase gradient a lot. What else? What do you want to do math? We haven't done any math yet. So I'd like to look at math-wise.
You used to talk about when you have to convert to different units.
For what section?
All sections.
Well, what units do you have to convert in what sections? Because
We need to convert in section, I think 25 this is when it's
like electron volts and joules?
Yeah.
That one you definitely have to convert. Yeah. You want to talk about the conversion factor and how to do it?
I know how to do that one. I mean, are there any more? What else?
So in chapter 25.1 and 25.2, you're going to use this formula here, right? Now, to figure out what the E value is, though, you're going to have to use this formula. If it's hydrogen, we talked about negative, I think it was 13.6. I don't want to give you the wrong number. What is it? 13.6? Thank you. Okay? But the units that you get from this top formula are electron volts. So this equals, based on the number of shells you are away, this equals some number of electron volts. Well, then you have to take the electron volts and recognize that 1 electron volt equals 1 times 10 to the negative 19 joules. So you want to take your answer, you get an electron volts here, convert it to joules before you use it in this equation. Remember that this equation is really delta E at the bottom. Okay, it's really a delta E. It's the change in energy. So if I'm an electron and I get excited and I jump up from level 2 to level 6, from level 2 to level 6, I should calculate E2 from this, and then calculate E6 from this, subtract the 2 to figure out my change in energy. My change in energy. Okay, this formula really has E sub n, the subscript, but it doesn't matter, it's there. Alex? Okay. So when an electron gets excited, it jumps up energy levels. But eventually it comes back down to what we call ground state. And when that happens, we have what's called spontaneous emission. That's the concept that when an electron loses its energy, because it's dropping back down to ground state, where does it go? It gets emitted in the form of radiation. Radiation with a certain frequency. With a certain frequency. This was proven really from the atomic spectra. If you remember Bohr's model told us that each element has a unique bandwidth of a bunch of different colors of its atomic spectra. And it's like a DNA signature or a fingerprint for each element. And that's where this was widely used. So,
Are you doing thermodynamic problems? Is the second element you do negative 2, is that for the object that lost?
doesn't matter. Think about it. If I have a negative on one side of the equation and the other, is it the same thing? Because I can divide both sides by -1 and still have a true equation, right? So it doesn't matter at all. But if you want to be really specific, the part that loses the energy, right? That loses the energy should automatically become negative. So the part that gains the energy needs the extra negative sign. But it doesn't matter. You'll just get a double negative and it'll cancel. As long as one side is negative, that's all that matters. And that comes about from conservation of energy. Q1 plus Q2 in a closed system is 0. The energy gained by one is equal to the energy lost by the other. So when I move this Q2 over, it just becomes negative Q2 over here, and now that's gone. And you get Q1 equals negative Q2. Okay, very good. This is not given on your formula sheet, conservation of energy. It's given earlier in the year, MEI equals MEF, right? But you're not given this formula. On your formula sheet, you're given three different formulas, technically 3. Q equals MC delta T, and then Q equals ML with variations of that. It could be MLF, or it could be MLV. Tell me the differences in when you use these formulas. Why do I use some of these formulas? Give me examples, give me something like that. What is a phase change? Very good. So the bottom two are used for phase changes. So let's do a quick example. We're not going to compute it, but we'll talk about it. Okay, let's say I've got ice. I shouldn't even have said that. Let's say I've got H2O instead. I've got H2O, and I don't know how much mass. I don't care. We're not going to calculate. We're just going to talk. And it's going from 20 degrees Celsius to 80 degrees Celsius. So my question to start, this is a very, very good multiple choice question. Does H2O undergo a phase change, a temperature change, a phase change and a temperature change, or neither a phase change and a temperature change? Well, looking at it, you see a temperature change, so you know that's happening, right? So the real question is this a temperature and a phase change, or just a temperature change? Steve, what do you think?
Just temperature.
How come, Steve?
It doesn't reach boiling or freezing.
Yeah, boiling is 100, freezing is 0. If the temperature change doesn't pass the freezing or boiling point, it is not a phase change in addition. It is not a phase change. Now let's do this. Take a look up. I'm going to change 80 to 180. 80 to 180. Break it down into stages. Give me the stages that occur here. Alex, go ahead. Stage 1, Alex.
So, stage 1 is still water.
Good. From 20 up until what?
To,
Very good, Alex. It's all water.
and then from 100, that's where it starts phase changing.
Good. So a mix, we'll say. It's a mix of water and gas.
Yeah.
And then?
And then from is like temperature change.
Very good. Temperature change. Good. So we've got a temperature change here, a mixture of the two, water and gas, making it only a phase change in the middle. And then once it's all gas at 100, it rises up to 180 degrees Celsius. Now, that means I'm going to calculate Q 3 times. 3 times. In the first part, it's going to be, let me just write it down so we can see a little better. It's going to be Q1 equals MC delta T. Q3, MC delta T. Now, the C values are different, so give them subscripts, please. The temperature changes they turn out to be the same. Of course, that is not meant to be. Either way, I'm going to give them subscripts. They happen to be the same. Okay, the masses are the same, though. Unless I specify that it's an open system, and let's say you start with 15 kilograms of H2O, and after it starts to evaporate, you only have 10 kilograms left. Well, then you would use 15 for Q1 and 10 for Q3. But I'm telling you now, I'm not going to do a problem where it changes mass. So you assume the mass is the same. Q2 in the middle has a different formula. What is it? What's the formula in the middle? It's not MC delta T. M. MLV. Explain the V portion, M. Good. When it goes from liquid to gas or gas to liquid, it's either evaporation or condensation. Now, evaporation, latent heat of vaporization, that evaporation, vaporization, very similar words, right? The other one is fusion, LF. And fusion involves what state changes? Fusion, what are the state changes? You can answer. Liquid to solid or? Very good. Or solid back to liquid. Okay, if you want to memorize that one for fusion, think fusion is things joining together. Imagine like liquids all coming together to make a solid. I mean, it's not really the way you want to think about it, but it might be helpful. If you just remember V for vaporization, that's probably even easier, right? Some other stuff. I talked about the fact that LV is always bigger than LF. LV is bigger than LF. It takes more energy to heat up water to a gas than it does to cool down water to ice. So I can take 1 kilogram of water and try to boil it, and take 1 kilogram of water and try to freeze it. It takes a lot more energy to boil than it does to freeze. A lot more energy to boil than it does to freeze. But that's just a chemical property. LV is greater than LF for almost all substances. C1 and C3 are different, and in your table, make sure you know the words. What is H2O called in the gaseous state? In the gaseous phase? What is it actually called? Steam is the word for it. Your table uses the word steam. Steam is water that is boiled. Again, steam is water that is boiled. And then water that is frozen we call ice, clearly. Okay, so if the C value is involving water, you look up the C value for water, which is different than the C value for gas. Okay, for steam. There are different C values depending upon the phase that you're in. What would I do with my 3 answers for Q1, Q2, and Q3 at the end of this problem? M. I'd add them up, provided I'm trying to find the total heat. Right? If I ask you, does it take more energy for you to gain temperature in this problem or to change phase? Well, then you have to sum together the 2 parts of temperature and see if that's more than the energy you needed to change phase. So I could vary the problem up for sure. It doesn't have to be written the exact same way. And it does not have to be written the exact same way. I could tell you how much energy is used and have you guys figure out maybe the mass. Maybe that's the unknown. I could say the total amount of energy is this. In your 3 equations here, we'll have M as unknown. It could be like M times some number, plus M times some number, plus M times some number, equals. And if I give you the total amount of heat needed, say equals 20,000 joules. So you have this number with an N, this number with an N, this number with an N, equals 20,000 joules. Combine your like terms with M, and then divide by the answer to get the mass. So what I'm getting at is that these problems can be varied a little bit. They can change based on what you're actually looking for. Okay, the same thing goes for calorimetry problems. This is a heat gain or loss problem. and a phase change problem. But calorimetry problems are very similar as well, and that had to do with Q1 plus Q2 equals 0. You could be asked to figure out what is the unknown substance. How do you figure out what the unknown substance is? What variable in these formulas involves the substance itself? Is the mass a function of the substance? No, it's a function of the matter. Is the temperature a function of the substance? No, it's a function of the average kinetic energy of the molecules. The C value. So if I ask you to determine the unknown substance, you're really finding C. You're finding C when you're finding the unknown substance. And then once you get the C value, look at the table. Which one is it closest to? Maybe you get 1.99 and the answer on the table says that it's 2. It's pretty much the same thing, right? What is it closest to is what you're trying to determine. The actual specific heat capacity, C. So depending on the problem, this can change, right? The arrangement, the setup, the attack you take, that could change. It could change. I'm trying to think of what else from this section. Oh, one thing that has been in a couple problems that students seem to get struggled with, and it could definitely show up as a multiple choice. Okay, definitely could. Is a problem where we don't have a temperature change, but only a phase change. And the reason students keep getting thrown for a loop on these problems, and I think it was one of the examples actually in the problems here, it always starts and ends at the same temperature. If it's only changing phase, it starts and ends at the same temperature. So if I said, how much heat is needed, right? How much heat is needed to heat up water at 100 degrees Celsius to steam at 100 degrees Celsius. And let's say it's 10 kilograms or whatever the mass is. So how much energy would it take to heat up 10 kilograms of water at 100 to steam at 100? Do you see a temperature change there? Absolutely not. So what happens is this. You're starting with water. You apply heat below the water. Heats it up, heats it up, heats it up. It's a mix. It's now water and steam. It's more steam, more steam, more steam until it's all steam at the end. So a problem like this would literally be the following. And you're done. That's it. There is no temperature change. If you don't see a temperature change, you can't use delta T. You can't use delta T. You don't see a temperature change. Don't put 100 in for delta T. Students see this problem, they put 100 in. It's not a change in temperature. It's a steady temperature. It's a change in phase. Well, yeah?
So like you said, it would be like multiple choice. It would be like Q equals MC equals me and like others.
Or I might actually make it a number problem. It's a very simple calculation. So if I do a little bit of math and multiple choice, you just type in 10 in your calculator, multiply by the table value you look up, and you can get one of the multiple choice answers. Or I could say, which of the following formulas would be utilized to calculate the amount of heat needed to do this? And then those formulas would be listed. And I might say MC delta T plus MLV, MLF, MLV, MC delta T plus MLF. You see how I can vary the choices up there? Okay, depending upon what's happening. So if it starts as ice, and it becomes water, that's going to be MC delta T plus MLF plus MC delta T, if there's temperature change on both phases. So think about these problems the way you think about them mathematically, but they could show up as multiple choice when it comes to change the phases and states. 5 minutes or so. We got a couple minutes left. Ask some questions, please. Did that answer your question? You kind of had a half hand up as well. Yeah? Okay.
So no temperature change, just phase change.
For this example. For this example, right? Only for this example. What else? What else? I'm trying to think of mathematical stuff that could show up that we haven't discussed yet. Chapter 10 is mainly the stuff. Oh, Chapter 10 also involved using your temperature scales. I mean, that's a very simple math, but you got to be able to convert. A real simple math problem on the test, or even a multiple choice, might say something like, you know, the temperature goes from 20 degrees Fahrenheit to 70 degrees Fahrenheit. What is that as a change in Celsius? Right? So 20 to 70. You can't just make that a change of 50 in Fahrenheit and then plug it into your conversion. You got to find the temperature at both stages and then subtract the two. Okay? So if I tell you like you have a certain temperature in Fahrenheit and then a certain temperature later on in Fahrenheit, convert both of those temperatures to Celsius, get your 2 new Celsius temperatures, and then subtract the 2 to see what kind of a temperature change it causes on the Celsius scale.
What's the difference between doing that and just taking 50?
Remember the y-intercept? Remember the formula? TF equals 5/9 or whatever it is, 5/9 TC plus 32. It takes into account the 32. Without doing it, it wouldn't actually be right. You don't want to be looking at a conversion. If you know your conversion, though, you can do it. Like I happen to know that for every degree Celsius, it equals 1.8 times every degree Fahrenheit. That's the 9/5. That's where that comes from, the formula. So it works out that if you had a 50-degree temperature change in Fahrenheit, you could just multiply that by 1.8 to see the temperature change in Celsius. That'll work fine. But if you're going to plug it into the formulas, you got to plug it in twice and then subtract the 2. What else? We talked about stability in the nucleus, what makes it stable. We talked about the strong force being a force that supersedes the electric force. Remember the protons, they don't want to be near each other. That's repulsive. The electric force wants to make the nucleus split. But the strong nuclear force, which is an attractive only force between the neutrons and protons and all the nucleons in general, causes them to stay together. The problem becomes when the nucleus gets so large that the nuclear force doesn't work as much anymore because it only works on small scales. Really close distances are where the nuclear force exists. It's like, imagine like honey, something that will keep things stuck together. But as soon as you have a bigger object, it doesn't work as well. That's like the nuclear force. It sticks and binds it all together, but only for really small locations, or small size, like a smaller nucleus. I gave a demonstration in the other section, which was pretty useful. I said, think about it this way. When nuclei are pretty small, the strong nuclear force is pretty strong. As they get bigger, it doesn't get as much stronger. The electric force is not as strong when it's smaller. But as they get bigger, it continues to increase. And where they cross over, that's like my threshold. These are stable. And these are unstable. Again, the blue is repulsive. It is the electric force. The red is the attractive force. And that is the strong nuclear force. So if the strong nuclear force is more than the repulsive force, it'll stay together until you reach what's like a break-even point. And then after that, the repulsive force is more than the attractive force, and you have radioactive decay. You have radioactive decay. I'm not going to get into stuff like half-life when you go into that. That's section 26.3, I think. No, 26.2, I think, actually. And we just, based on the days we had left in the schedule, I didn't include that section. It's not a tough section, but it's not included on your test based on time.
Why do we learn about this stuff in physics?
Because if you really wanted to do the chemistry that's involved in this, you need to be like a nuclear physicist. There's a lot of physics at the subatomic level, way more. Like this is just a certain. So if you want to be a nuclear physicist or a nuclear engineer, this is like basic 101 of what you need to know. So this is just an introduction to it, that's all. But you do a lot of chemistry in engineering, not just physics. Engineering is a combination of chemistry, physics, and some biology, not as much, and then a lot of applied math, a lot of heavy applied math. So if you're going to study something like that, you need chemistry and physics to understand what's going on in the nucleus. Especially beyond that, sometimes. So this one up here is the electric force that's pushing the nucleus apart. That's the protons wanting to repel each other. That's the force, remember K, Q1, Q2 over R squared that we learned earlier in the year. That's what that is. This is called the strong nuclear force. There's also something called the weak nuclear force, which is totally different, which is not something we even went into. And then you have gravity. Gravity is the weakest of the forces. Isn't that crazy to think about that? It holds us together, yet it's the weakest of all the forces. Magnetism, electricity, strong force, strong nuclear force, weak nuclear force are all stronger than gravity. Yet gravity is what kind of regulates everything in the universe somehow. Right? Isn't that crazy to think about that? In magnitude, it's so weak that it really regulates everything.
Gravity is weaker, but then we can move it.
Yeah, thank God, right?
Yeah.
If it was too strong, you'd be like stuck to the ground. If it was too weak, you'd kind of be floating. It's just right, I guess.
Yeah, and also, do you have to know about this, like the charge of there,
No, but this is a visualization of what's happening. As the nucleus gets bigger and bigger and bigger, so the x-axis is the size of the nucleus. As that continues to increase, this is the amount of force it feels. And what happens is, as it gets bigger and bigger, the nuclear force doesn't keep increasing as fast as the electric force. And eventually the electric force is too much, and that repels the protons, and it gets split apart. That's why we call them unstable over here and stable on the left side. Okay? Please make sure you study real hard. You have this test and you have a project. That's it for the year. Nothing else is left for your grade. So if you really want to get that boost and you need like a certain grade to get above 80 or above 90 or above 70 or whatever your goal is, keep that in mind. This is your last shot here, and then your projects are due on Monday. Don't forget about those projects, please.